Okay, good morning, everybody. My name is Jose Torralba. I'm going to present you the paper entitled Lattice Distortion Study in Gamma Prime Cobalt-Based Superalloys produced by Powder Metallurgy route with low tungsten content. This work has been made in collaboration with other people, Marta Cartón and Elena Sanz and Mónica Campos from University Carlos III of Madrid. Marta Cartón is now working at CENIM in Madrid. And also with the Professor Song-Ji Hong from Korea, from the Konju National University of Korea. They have provided to us the powders. So in this work, we still work in the new cobalt aluminum tungsten system. It's a new generation of superalloys, cobalt-based, in which we try to compete with the nickel-based superalloys, developing a gamma prime microstructure. But in this new family of cobalt-based superalloys, we have developed a gamma prime precipitase, and in this way we can assure a good behavior at high temperature similar to the nickel-based superalloys. But we have to solve some issues in order to improve this good behavior at high temperature. The most important maybe is the high density of these materials, because in atomic percentage we have in the order of 9% of tungsten. So it's interesting to reduce the tungsten in the composition, and also the anomaly flow stress of the precipitase, the gamma prime precipitase, are a little bit lower, as you can see in this picture, than the conventional nickel-based superalloys. So that means that we have to do things to improve this behavior at high temperature. So in the European 2018, we presented a work regarding to these materials, in which we develop these new cobalt-based superalloys produced by atomized powders. So in that case, we got very nice microstructures according to the expected microstructure that we need to have a good performance at high temperature. These materials were compared with the materials also produced by mechanical alloying, and in this graph we can see in the bottom part the conventional nickel-based superalloys, and here the different alloys developed by us with tungsten and aluminum, in which we see that if we perform some heat treatments, we can improve the level of the yield stress at high temp, even maintaining this high level at high temperature. We have to try to explain this, what happens, and we have to analyze or to study how to improve the performance of these alloys. So the classical approach to the strengthening mechanism in superalloys are these first four things. First, the solid solution strengthening. We can improve the strengthening by solid solution. We can strengthen by gamma prime precipitation, as we did in nickel and in these new cobalt alloys. The carbide strengthening and the grain bonding strengthening by some elements like boron or even carbon in the border of the grains. But we have to analyze new approaches to understand this good strengthening in superalloys. One is the strengthening due to the dislocation interactions, and the last one is the so-called coherency strengthening. How is the coherency strengthening? What is the coherency strengthening? We can evaluate it through the so-called lattice misfit. The misfit can be calculated with this formula, in which we have here the lattice parameters of the gamma and the gamma prime, and we obtain this value that could be positive, negative, higher or lower, depending of these lattice parameters of the gamma prime phases. The coherence in some way increase the hardness or the mechanical properties due to the level of the coherency. Here we have different levels of coherency. Here we have two phases completely coherent. Here we have a coherent lattice with some tension. This is a semi-coherent material. This is coherency, but very different size of the atoms. In that case, we have some tension in the lattice. Also, we can have the semi-coherent materials. Here we have this semi-coherency in this direction, but not in this one. For this reason, we mention it as semi-coherent, and we have a completely incoherent material. In that case, we will have a higher lattice incoherence and a higher misfit. So also another interesting thing is that in the case of gamma prime superalloys, as much as we increase the incoherency, as much as we increase the misfit, the size of the precipitates tend to be more square than spherical shape. So another interesting thing is that if the lattice misfit is positive, so that means that the network parameter of the gamma prime is much higher than the gamma. We used to have dislocation activity in the parallel channels of the gamma phase, in the parallel channels to the applied force. So that means that we have a more efficiently way to prevent the dislocation movement, and in that case, higher mechanical properties, especially at high temperature. And if this lattice misfit is negative, then the network parameter of the gamma is much higher than the gamma prime, and then the dislocation tends to move in the perpendicular channels in the gamma matrix. So that means we will have, in principle, worse mechanical properties. What we have done in this work, we have applied heat treatments. We have analyzed the microstructure, we have evaluated the microstructure, and also we have performed a mechanical property at room temperature, which is the universal hardness. So this is the experimental process. We have gas atomized the cobalt 9 aluminum 9 tungsten. This is the microstructure of the powder. Then we have consolidated these powders by field-assisted hot pressing at two different temperatures for 10 minutes, applying 50 megapascals. And then we have homogenized the powders after 12 hours of 15 degrees. And we perform also an aging treatment after the homogenization at 900 and 1000 in the case of the 1250 synthesis material, and only 900 in the case of 1400 synthesis materials. Here, more than that, we have assessed the lattice parameter by X-ray diffraction. We have analyzed the microstructure, and also we have measured the volume fraction of the gamma prime precipitates and also the size of these precipitates. We have measured these two dimensions in the square precipitates, and as you see here, the length of the A and B parameters are different depending on the treatment and depending on the sintering temperature. Here we have one scheme about how we have developed the universal hardness. We have measured the indentation peak, the load of each sample, and also the indentation depth, the maximum one, and the plastic deformation depth that we have after one indentation. We can calculate this universal hardness by this formula, in which we introduce these parameters into the formula. This is a quite located mechanical property, so if maybe it's just to give us an idea of the general mechanical properties, but we have to perform also hot compression tests at high temperature in order to see how the misfit really affect to this property at high temperature. Anyway, we have developed the microstructural analysis, the gamma prime volume fraction measurements, the misfit evolution, and also some hardness features. Here we have the microstructure for the sample sintered at 1250 in a sinter state, homogenized and aged at two different temperatures. You can see that we can see perfectly develop the cuboid structure for the gamma prime precipitates. If we see it at higher magnification, it's more clear. You can see here how maybe this is the highest size of the cuboids, as we will see later, with more detailed study. And also for the higher temperature, we have very well structure developed with the gamma prime cuboids precipitates on the gamma matrix. At higher magnification, we see some clusters of gamma prime with some bigger channels of the gamma phase that maybe will affect to the behavior at high temperature. So here we have the comparison between the gamma prime size in the different stages, in the material sintered at 1215 and in the material sintered at 1400 degrees. Here we have the A and the B parameters, and you see that we have maintained more or less the same level of the size of the precipitates. Only in the case of the materials homogenized at 1400 degrees, we have a higher level, a higher size of the gamma prime precipitates. If we also analyze the volume fraction, we have similar volume fraction for the materials aged or homogenated, but a little bit higher for the homogenization process. So also we have performed the diffraction patterns of the samples consolidated both at 1250 and 1400 in order to get the lattice parameters for the gamma prime and the gamma. But if we see the conventional diffraction patterns, we see that we have a very well-defined peaks for the gamma and the gamma prime, but take into account that the both peaks are overlapped, it's difficult in these images to have to measure the real lattice parameter of the gamma or the gamma prime. For this reason, we have to deconvolute. We have to produce a deconvolution in order to distinguish the peak of the gamma and the peak of the gamma prime in order to calculate this lattice parameter and then the misfit for each material. Here we have a summary of results for the material sintered at 1400. Later we will compare with the 1250 degrees sintered materials, but here we have the three different indentation figures with the load and deformation graphs, and also here we have the calculated earth strength, which is in some way proportional to the Young modulus of this material in the sintered state after homogenization, after aging. You see here how the highest value is the material in that case for the homogenized material, which was with maybe the higher level of gamma prime volume fraction and size for the gamma prime precipitates. Here we can compare all the results. In that case, here we have the best mechanical properties for the higher value of the misfit, but it's not the same for the 1400 degrees, maybe due to this strange microstructure with those channels for the gamma matrix. We should perform some tests at higher temperature in order to check how the misfit really affect to the high temperature properties. If we come back to this figure that we proposed at the beginning of my talk, in which we have in a previous work how was the behavior at high temperature, we can check how those materials with higher misfit, who was the homogenized and the aged material, has much higher values for the yield stress at high temperature than the material sinter or other materials from other different consolidation methods. So after these results, we can produce some conclusions. And the first one is, of course, that the feasibility of the powder metallurgy route to produce gamma prime superalloys with a proper structure to have a good behavior at high temperature. Of course, if we produce heat treatments after the sintering, we can manage better the size and the distribution of these gamma prime precipitates. So in this case, we can in some way tailor the microstructure to obtain good performance at high temperature. So through the heat treatment, this gamma site can be modified. And of course, as a consequence of this modification, we can modify the mechanical properties at high temperature. The consolidation temperature is also affecting the gamma prime volume fraction, as we have seen. And in this work, the gamma prime volume fraction increases when the consolidation temperature was elevated till 1400 degrees, but with a relatively low misfit coefficient, similar to the previous obtained for the 1250, but a little bit lower. To obtain higher volume and size of gamma prime precipitates, of course, the heat treatments are the key parameter. So with this heat treatment, we can try to increase this gamma prime size and distribution. So we have obtained, not in this work, because we have developed here only hardness, universal hardness, but in the previous work we have seen that we can reach really very good results for good performance at high temperature, and we can assure that PM route can promote the formation of secondary phases with the typical, without the typical segregation casting process, and we can compete perfectly with the ingot metallurgy of nickel-based superalloys. So powder metallurgy here offers a lot of advantages, not only in terms of the processing method, but also in terms of the tailor of the how we can tailor the microstructure, how we can tailor the composition. So just I would like to finish, just give some acknowledgement to the Pilot Manu project, which was funded by European Union, that led us to develop this work on cobalt-based superalloys. Thank you very much.